No question? Okay, so do you understand the concept of you know this potential energy surface?
So contour
What?
lines वगैरह.
Yes, hello,
So
Sarthak,
potential
what did you
energy
say?
surface as in contour lines and all.
What? Sorry,
Am I audible?
uh, your voice. Your voice is not clear. You are audible, but voice is not clear. Just tell me again.
So like by potential gradient, you mean like contour lines and all, or something else?
Yeah. That's same thing. Yes, that is also known as potential energy surface. Okay. So what I mean by this is this picture. This picture. Okay. So this is also known as potential energy surface. Okay. So you need to keep in mind that from one side it is minima, and from the perpendicular side it is maxima. And transition state. I am talking about transition state, and transition state is known as saddle point because from two different perpendicular sides, um, from one side it is maxima and one side it is minima. So, but reaction energy pathway is like this, okay, and state is maxima in reaction pathway. Okay, so any reaction wants to go through minimum energy pathway, and transition state is maxima in that pathway. Is this clear? Okay,
Yes.
this diagram I have already shown you that it looks like this. Okay, and this is your basically reaction pathway. And from one side, if suppose this side is reactant, this side is product, so you are going from this pathway, and here is your transition state. From this diagram, you can understand a bit about why this looks like potential energy surface looks like this. Uh, so here is it is quite analogous to when you are trying to go from one valley to another valley. You would like to take a pass, reaction is like that. So reaction will go from this valley to this valley, or from this valley to this valley through minimum energy pathway, and this is analogous to pass um, between two uh, hills. Okay, this is your saddle point, and that is also known as transition state. Okay, so this is your contour map. Contour map is simply what you are trying to do is uh, to show three-dimensional picture on two dimensions. Okay, so basically you cut this three-dimensional picture at different value of Z. Here Z is your potential energy, and then you just squeeze it. So this is basically to show one contour basically shows all the point uh, all the point in this diagram, 2D diagram, all the points with similar potential energy. Okay, or similar energy. This one is again all the points with similar energy. So, okay, so this is like this. Here you can see that RBC is maximum and RAB is also maximum. So this shows you where almost all ABC is um, far apart. ABC atoms are far apart. Okay, so all atoms are dissociated. In this side, you can see RBC is small and RAB is small, and so this represents when you know ABC. This distance is this distance is these two distances are less than equilibrium AB or BC distance. So this side is that. So this is basically your reaction pathway, and here is your saddle point, which is known as transition state. Okay, so contour plot. If you want to see, you can go to Khan Academy, and then you can see this thing. But it is simple. Idea is not very difficult to understand. One more time, I will show it. You. Okay. Let me just so okay, so I think that there are problem with internet. Anyway, so now you understand, I believe, contour plot. Am I right?
Yes, sir. But like, मतलब उसमें doubt like अगर you give a 2D plot, then it would be hard to tell कि like where is the saddle point. Like that part is a bit weak. I think. Like I can understand that in contour plots, wherever there are things which are close to each other, the lines that means it's like a maxima. Like there's a steep slope there. I can tell that there's a steepness if their lines are like close to each other. But then I can't tell that what kind of path will it take if you give a map. Like I won't be able to tell it that easily.
Okay, actually, I didn't understand your question quite very well, but it is simple that if you go here, say this, right, and then you start cutting it.
Yes, I understood that. I'm saying that if a 2D contour plot is given to me, then it is slightly difficult to tell the exact path with the which the reaction will go in.
Okay, so it is not that difficult. Let me show you to you. Okay, so this is your thing. So it will certainly here, you see this. This is your equilibrium distance for BC. Okay, RBC. Here is the equilibrium distance for BC. That energy you know all. Right? So
Yes,
you
sir.
will start from here and then it will go up and up. Because here energy is increasing. Okay, energy is increasing. Energy is increasing. And then here it will be maximum. So you are going in this path. Right? And then again energy will start decreasing. And that's what you see as something like this. Okay, energy increasing, increasing, and then it goes down. Okay, and this point is basically this, right? And I also told you that this is the lowest energy. Hence, you are more towards this side. Okay,
Yes, sir.
and then energy is increasing. So that's what happens here. Energy is now increasing, increasing. Okay, you cannot start from here because this will not have. You see, if you are go to this point, then energy is high, right? Compared with this one, this. As you go far, energy is high. Okay, so you will not go to a path where energy is higher. You will take a lowest energy path. That's what you are seeing it here. And from this diagram, you can know if I go this side, what happens. This side, both RAB is also high and RBC is also large. It means A, B, C quite far apart, so dissociated. Here it is quite closer. Then RBC equilibrium is what? This one, right? And this is RBC, this distance, bond length, you can think. RBC is equal to bond length between B and C. And this distance is bond length between A and B. Okay? A and B. So if you are this side, then what does that mean? Distance is lower than both RAB and RBC at equilibrium. Okay, and so this part shows you repulsion part, and this part there is no interaction between A, B, and C. So and this is minimum energy pathway, and this is basically you are talking about between two hills.
So,
Is
but
this
if there are
okay?
hills, then that should also be high contour. Like it should be very congested, right? The lines, because then only the
So,
steepness would be shown.
so think about like this. Okay, this side is there is repulsion. Here you are quite far apart. Okay, so this is kind of this thing. Here there will be repulsion term, and here there is no interaction. So this represent basically if you go in diagonal line, you are going from this side to this. This is your repulsion where this side and this side is your there is no interaction. So between two hills you are going, and as you go, suppose there is no interaction here, and as you bring together, what will happen? Energy will start to drop because of attractive forces, right or not? Attractive forces, and then what will happen when now R AB is less than RAB equilibrium, or bond length between AB and RBC less than bond length of BC, then
Repulsion.
repulsive forces starts. So that's why energy starts increasing. So you are between two hills. Is this clear?
Yes, sir. Like the only thing was that in those two other hills, like I felt that if the line should have been more closer, then I could understand that there's steepness. But now I can't tell if it's a hill because like the
Yeah, so it may not be a very good diagram because it is a handmade diagram. But simply think about that in this line, if you go from this side
yes,
to
sir.
this side,
Hmm.
you are going between two hills.
Yes, sir.
Means one hill, then drop, and then further there is also. This is one hill, there is second hill, in between you are trying to go.
Yes, sir.
This okay?
Yes, yes.
Does that make sense? Yeah. So this
Sir,
is
So
this is
does that
some. Yeah, please. Yeah.
does that two hill you represented in the handmade diagram in the
Mm-hmm.
sixth slide, these two
Six.
hills, uh, is this red color in the 3D diagram in the fourth slide?
This is a part of hill. You can think about this is a hill. This side there is a hill, and this side there is a hill. Okay, so two hills. Between two hills you are going. Is it
I
clear?
am
This represents one hill, and that side is one hill.
I am talking about the 3D figure which is given in the fourth slide.
Fourth
Does the
slide.
two hills
Yeah,
does the
this one.
two hills represent the reddish part?
Yeah, you are right. Yeah, this is one hill. This side one hill. One side repulsive forces are predominant, and one side there is no interaction.
Okay, sir.
Is this okay? This thing we are talking about,
Yes, sir. I got
right? That's what is. If you go in here, this represents this side. Okay, diagonal
uh,
line. Okay.
sir,
Yes.
will we always have these side plots along this contour plots to tell if it's a valley or a hill? Because the contour plots of a valley and a hill might look same, no?
Can you again repeat the question?
So the two side plots which are made, the one at the top and other at the right, are these the part of the contour plots?
Yeah, yeah. So you see this side. Basically, here you are dealing with. You see, RBC is quite close, and RAB is very high. It means what? That BC, there is a BC bond, and A is approaching from quite far. So this will be your energy. As it come closer, then energy will increase. Okay, so that's what it
Yes,
is
sir.
showing it here. Right? And
Yes, sir.
then it this side is, if you go here, so what does that represent? AB, there is a AB bond and C is approaching. So this point is where there is bond between A and B. Okay, that
Yes,
is the
sir.
distance at which this is the distance where uh, RAB is equal to RAB equilibrium. Okay, means there is a bond which is normal bond distance, and C is far apart. This shows you BC bond and A is far apart. Okay, so you are going from this valley to this valley, and I told you that this is the, if you compare between all these lines, this is in negative value, this will be larger, or lowest energy value you can say. So this is lowest energy. After that, a bit higher energy. This is a bit higher energy. So you are going up and up and up in energy, but after this point, this is the highest point, and after that it has started decreasing. Is this okay? And you go opposite way. So you start with AB bond, and C is approaching, then you will go like this. Okay. This is the reaction path. You are going from lower energy to high point and then again to lower energy. So it's something like, it looks like this. So AB plus C and A plus BC. Okay, so this side is AB reacting with C, this side is A plus BC. Is this okay? Is it clear?
Yes.
Okay. Anybody else? If they have question, please just ask. This is a very important concept in kinetics, potential energy surface. And contour maps, you will come across contour maps in different areas. So please understand what we mean by contour maps. It is just representation of 3D plot on 2D. Okay, a lot of time you will come across this kind of representation. Is this okay? So yeah. Okay, so let us go, and this is our potential energy surface, and now you know that why this activation energy plot looks like that. So now let's move to catalysis. What is catalysis? Okay. So till now you have we have discussed how to get rate constant, how to find out mechanism, and then now we are going to catalysis, which is a very important thing because most of the reactions needs the use of catalyst. And if you look at our body, all the reactions which are going on is basically catalyzed reaction, and that's why they take place at room temperature and pressure. Okay, atmospheric pressure. So what is a catalyst? Catalyst basically accelerates reaction by stabilizing a transition state. So now you understand what is transition state. So by stabilizing a transition state relative to ground state. Okay. So if you take up this normal reaction, which is like this, then what catalyst does that it decreases the activation energy. So it decreases the activation energy. Okay. Or delta G, sometimes you can also write delta U, but now since we are talking about total delta G, because it is delta G which determines the stability, so we are also including the entropy part. So basically if we plot G versus reaction coordinate, then delta G star is this, the difference between free energy of reactant and transition. So this is your delta G, yes, and this basically increases either for forward or for a reverse reaction. So rate constant will increase. Again, rate constant for both forward and reverse reaction will increase. Okay, but energy of reactant and products are uh, not doesn't change. What does that mean is delta G value, which is this one, will not change. It means if you take delta G naught, so it means K will also not change. So equilibrium constant doesn't change. So please keep that thing in mind, that it doesn't affect equilibrium constant, it only affects the rate. Okay. How does this catalyst work? That's what we are going to understand. One of the concepts which has been put forward is differential binding. It means binding to different species to different extent. So it is like this. A is so this is reactant, this is catalyst. First there will be intermediate form A dot cat, and then it goes to P dot cat, and then finally your product is formed. P is product, A is reactor. So there are 4 scenarios which you can think of according to differential binding. So here you see what is happening in this case. So this is your A, this is A dot cat, this is your P dot cat, and this is your P. So you have similar things in all 4 diagrams. So please keep that thing in mind. Now what happens here that when A when catalyst binds A, then energy of this reactant decreases. Means it becomes more stable, but it is not affecting the the transition state. So what happened that you see this basically delta G, this has sign cat, it basically increases in presence of that catalyst. So in fact in this case you will not see the increase in rate of reaction because now activation energy is more comparison to this activation energy when there is no binding agent. Well, let's doesn't call this cat. We have written cat, but this is basically to show it any compound which binds and affects the activation energy, but doesn't affect the energy of free energy of A and B. So this is not. So in this case, you did see that rate of reaction is not going to change, and hence this cannot act as catalyst. In the second case, this is binding destabilizes A, and so energy is high. Okay, energy is high. But again, in that case, your transition state is not affected. So overall, the activation energy doesn't change. And that's why, again, this kind of binder cannot act as catalyst. Okay, now let us go this case. Now here, your catalyst, the binder, let's say binder, affects the reactant and transition state, but reactant is more stabilized in comparison to transition state. So delta G has increases, not decreases, and that's again will not be taken as a catalyst because this will again lead to increase in rate constant. Now this is the fourth case in which reactant is stabilized, transition state is stabilized, but now stabilization of transition state is much more in comparison to stabilization of reactant, and so the activation energy will decrease, and hence rate of reaction will increase. From both sides you can see that activation energy decreases, but now you see that reactant and product energy is same, and so equilibrium constant is not getting affected. So this is one of the hypotheses why a certain compound act as a catalyst. So differential binding to accelerate a reaction, if we want acceleration of reaction, a catalyst must stabilize the transition state more than it stabilizes the substrate. Okay, so this is very important point which you need to keep in mind. And that is again shown it here. So this is A, this is A cat, this is P cat, and this is P, and this is your transition state. And activation energy decreases, and so your rate of reaction will increase. So that was first hypothesis, but there are other hypotheses also. So that is known as catalyst by approximation. catalysis by approximation. So what catalyst does is it brings both reactant quite close to each other. And when reactants are quite close to each other, it basically increases what is known as effective concentration. Okay, and orientation is also quite better, and that's why the rate of reaction will be higher. So how does it increases effective concentration? By bringing together the reactants. So please keep that thing in mind. Okay. In that case, there will be loss of entropy because both reactants are quite closer, but that will be compensated by intrinsic energy of binding. Okay. Magnitude of this effect is given by effective concentration. That's what I was saying, that when you bring two reactants together, then this leads to a better binding, and so effective concentration increases. And that can be calculated by looking at rate constant of bimolecular and intramolecular reaction. So I will give you one example to you. So it is in energy term, it is simple that this is intermolecular reaction A plus B, and suppose there is a catalyst in between and A is nearby to B. In that case, what happens that intramolecular things we are looking at. In that case, there is trade-off between enthalpy and entropy, and basically free energy of the reactant will be smaller, means larger, higher, and so this delta G has value will decrease. It means activation energy decreases. Okay. Now we will show it by example. Let us see. So this is one of the example of catalysis by approximation. So look at this reaction. Okay, and then this is CH3COO and this thing. Okay, plus in CH3 thrice. Alright, so this is reaction with a base. The observed rate constant is 4.3 or 43. Okay, so 4.3 per molar per second, and this gives you this reaction. This is product, and here are A and B are reactor. So this is intermolecular. Okay, so it is like A plus B. Now what happened that if you take, suppose this reaction and this is same reaction is taking place, but now it is intramolecular reaction. In that case, you see rate constant increases by 5,000, and that 5,000 is known as effective concentration. Same reaction, one is happening through intermolecular and another is happening through intramolecular. Okay, so this is intermolecular, that's what I was saying, and then intramolecular. So here you have intermolecular and this is intramolecular, and you can see that rate constant, same reactions. You can see A and B are just in a same compound. In that case, even if you take same concentration, okay, rate of reaction is going to be very high in intramolecular one, and that is because of now effective concentration is quite high. Okay, in this case, in first case, it is quite far apart. A and B are far apart, and so effective concentration of these two species is not that high. In fact, they went ahead. There are a lot of studies in this field. So look at this reaction and consider that K relative is 1. Same reactions now is done in intermolecular fashion. intramolecular fashion. You see, this went to 220 per second. In this case, it has gone to 5.1 into 10 to the power 4. In this case, it has gone to 2.3 into 10 to the power, I believe, 6. And in this case, it is 1.2 in 10 to the power 7. So effective concentration, you look at this. All right. So this is just effect of intramolecular interaction. Okay. In same molecule, both A and B are present. In that case, rate of reaction will be quite high. And that is the concept behind what is known as effective concentration.
So with the
So
catalyst, rate of reaction increases, but rate constant remains same, right?
Rate constant, no. Equilibrium constant remains. Rate
Equilibrium.
constant will change.
Will increase.
This is rate constant.
Yes.
Okay, this is rate constant. Rate constant will change. Okay, rate constant is increasing. You can see here.
Yes.
Right. What will not change is equilibrium concentration.
That's because energy of product and reactant are
Reactant is
same.
Okay. So please keep that thing in mind. This is very important. Why catalysis takes place. So basically, what it does is catalyst brings A and B together, and so they increases the effective concentration, and that's why they increases rate constant of that reaction and rate of reaction, but certainly it doesn't affect the equilibrium constant. Okay, so next is third hypothesis is known as covalent catalysis. What it does is it forms covalent intermediate which reacts faster than uncatalyzed reaction. So this is not about energy, it reacts very fast than uncatalyzed reaction. So AC is more, what you can say, AC is more reactive in comparison to A. So that is the third hypothesis regarding catalysis. Okay, so let us see if we can talk about it. So here you can see that this is A and then AC is formed. Okay, and then reaction happens. So A to AC formation is faster because this activation energy is lower in comparison to this one. Okay, so this is known as covalent catalysis. So in order for catalyst to be efficient, the activation energy for formation of intermediate, which is basically A dot C, this should be smaller. Okay, and this should also be smaller. Here you can also see that activation energy is to product formation. So in order for catalyst to be efficient, the activation energy for formation of the intermediate and for a subsequent reaction must both be lower than that of uncatalyzed reaction. Okay.
So could you repeat the point?
So what I'm saying, that activation energy of this, okay, for the formation of this is activation energy for the formation of intermediate, and the subsequent reaction means AC plus B. Both reactions, activation energy of both reactions must be small. Is this okay? Then activation energy of non-stable reaction. That's what
Yes.
okay. Now let me give one example. So here is this intermediate. So this is a compound, mustard gas basically. So chloride comes out, and now intermediate is formed with the positive charge, and we know that positive charge, this will be, water can attack here very fast, right, because there is a positive charge. So this is one example of non-enzymatic covalent catalysis. So this intermediate is very important. Formation of this intermediate is very important. This intermediate, so reaction, this reaction to this intermediate, activation energy is lower in comparison to if I go just from reactant to product. Okay. So enzyme uses nucleophilic groups and cofactors to form covalent bond. I will give one example to you. So look at this. This is hydrolysis of your amines. So this is protein basically. So this is your protein. So you can see CONH group and R2 is here, R1 is here. So it is alpha amino acid. This is a polymer alpha amino acid, and this is your what is known as aspartyl protease. Okay, in that there is 2 aspartic acid. Okay, so this is what we get in our body. Okay, how proteolysis can be done very fast at room temperature and atmospheric pressure. So what it does, that it takes this proton, makes this very good nucleophile that attacks here, and then this negative charge is accepted by this. So intermediate energy is very low, and so basically activation energy is very low, not intermediate energy. Activation energy is very low because of formation of intermediate, and that's why this things happens very fast. Okay. Similar case of this is aspartyl protease, this is cysteine protease. Again, you can see that this group histidine, and this is your thiol group cysteine basically. So this hydrogen can be taken by this, so this negative charge can attack here. So basically, you are trying to make this covalent thing. Similarly, metalloproteases, this X can take hydrogen, and this negative charge is stabilized by Zn2 plus ion. Okay, so this is example of Zn2 plus is there in all of metalloprotease. Means there can be other metals also, metalloprotease. So this is how a reaction is catalyzed in an enzymatic reactions. So the next one is similar thing, but nucleophilic catalysis. Okay, so what happens that you can see it is simple acid chloride to ester reaction with the alcohol. Acid chloride reacts with alcohol to give you ester. When you do in presence of this triethylamine, what will happen that it will form this intermediate. Okay, this intermediate. This thing is very fast, and then R-OH will be a beta nucleophile because there is positive charge here, so it can attack here, and this comes up. Right, this attack will be much faster. Right, because there is positive charge here, and then this electron can go to this positive charge, and there is a good leaving group. You can say there is a good leaving group. Have you heard about good leaving group?
Yes, sir.
Yeah.
Yes,
so this is much better leaving group in comparison to chloride ion, and that's what is happening. So intermediate is formed, and then this R-OH can attack quite easily because this is a good leaving group. So this is an example of what is known as nucleophilic catalysis, because here nucleophile can attack it much better in comparison to in acid chloride. Okay, so there are other examples. Let me show you one more example. This is decarboxylation. Okay, so CO2 groups comes out basically. So CO2 group comes out. That reaction also requires catalyst, and this also happens in our body mainly through different enzymes. For example, acetoacetate. This is acetoacetate group. So there is enzyme called acetoacetate decarboxylase. Okay. Again, you can see that this group will go here, and then this goes at this position, right? And you will get this, and finally you will get a keto group. But if there is catalyst, again here base can be the catalyst. So base comes out, and then it will this, so it will attack this double bond O, and then this will form. All right. This has positive charge. Again, this is a uh, you know there is a positive charge, so nucleophile has now more tendency to, because you see now this plus goes to, and you will get you know neutral molecule. If this CO2 comes out, you will get a neutral molecule. Here what you are getting, a negative charge molecule. So this will be certainly a much faster process. Okay, much faster process. Then H plus can attack, and then hydrolysis can happen. That's what is shown here. So this is another way of catalysis. Okay, what you are trying to do, just simply making now CO2 as a better living group, and that happens when there is a nearby, there is a positive charge which is in conjugation with this bond. Okay, so this is example of covalent catalysis. Nucleophilic catalysis is one subgroup among covalent catalysis. Then there are electrostatic catalysis. So if there is some charge and you somehow makes it more stable, then some catalyst makes this negative charge more stable, then that uh, can decrease the activation energy, and that's how they can increase the rate of reaction. So stabilization of charge developed at transition state. So that stabilizes and decreases the energy of transition state, and hence activation energy will decrease, and finally your rate of reaction will be much faster. So there are proteins called, enzymes called serine and cysteine protease. They favor formation of tetrahedral intermediate by stabilizing the negative charge developed on oxygen. Okay, so there is this minus charge, and then that can be stabilized by some of the amino acid here. So we will show some example. So here you see what happens, that there is serine. So this is serine protease. So serine is important. So there is a histidine here, which takes this hydrogen. This electron pair attacks at this position, and there is O minus form, and that is stabilized by these two amino acids. So transition state is stabilized by hydrogen bonding with these two amino acid of the protein. So these all three amino acid is part of that serine protease. Okay, that's serine protease. But idea is simply to stabilize the intermediate. If you stabilize the intermediate, it is simply like this. If you stabilize the intermediate, it goes down. So it is like this. Okay, that will be two process, but I am talking about first step. And so this is your intermediate. So this is activation energy now decreases from this value to this one. Okay, and that is the whole reaction. I'm not going to discuss about that. This is the structure. So there is a histidine here, a bit difficult to show, but this work has been published in a journal called Journal of Molecular Biology in 1991, and that's how they explained how this proteases work. Okay, what they are basically doing. These are all the things which I discussed here. These three groups: glycine, serine, and histidine. These are four from the same amino, same enzyme, and that is shown it here. This is histidine. Then a bit difficult to say, but here are those four amino acids which basically stabilizes the anion. Okay. So in this paper, what they did is they created this protein is called subtilisin. Okay, so that's what I was showing to you. And then what they did is they created mutants. So they changed that serine 221. If you remember, serine 221. This okay, I think this is the protein. Okay, serine 221 and histidine 64A and aspartic acid 32A. What they are able to see that, so these three are very important amino acid in that protein, this protein, which stabilizes the oxy ion. Okay, so this is known as catalytic triad. And if I change this, that is a possibility. Generally, it is done that serine at 221 position of that protein is changed with alanine. Histidine at 64 position is changed by alanine, and aspartic acid at 32 position is changed by alanine. Then what they are able to show that reaction catalysis rate of reaction is 10 to the power 6-fold less. So just think about these three are very important, and the role of these three are simply to stabilize the transition state. Okay. Even if I mutate this, the mutant is able to catalyze the reaction 10 power 3-fold faster than the uncatalyzed reaction. That is because of effective concentration thing which I told you. So 10 power 3-fold higher than uncatalyzed. But if these three are present, then it is like 10 power 10 power 9-fold more than uncatalyzed reaction. So important part of catalysis is due to electrostatic environment. This provides electrostatic environment. They form hydrogen bonds with the negative charge residue, and so they are able to catalyze the reaction. Okay, so metal catalysis. This I will talk in the next class. If you have any question, just let me know. Yes, any question?
There are these examples like for understanding, or should you remember them? Like,
this is for understanding things, how they can catalyze. So whenever you are designing a catalyst, you should keep these things in mind. So that is another area of research, that how to make catalyst. So you need to keep these things in mind, then only you will be able to synthesize.
so can you generally say that the catalyst makes a single step reaction into two step? Like if you
What?
a catalyst, it makes a single step reaction into two smaller, faster steps, right? Like by decreasing. That's
Yeah.
always general trend.
So
Catalyst.
certainly catalyst will get involved first with one of the reactant, and then the second this thing will come. So certainly it will be more than one step reaction. And I will discuss enzyme catalysis. Okay. Other catalysis also. So once I've given you a general picture of catalysis, then we'll go about the mechanism of catalysis. Okay.
Yes.
Any other question? Anyone? No? Okay, so then I will stop, and